Hopefully everyone can hear us. So I'm Alistair Willis, the Marketing Director for Geobear in the UK, covering UK and Ireland. And we've got Andy Lee, a Vice President of Engineering, with us today to talk about a slightly different topic than usual. If you've joined a few of these webinars in the past, we have some regular topics, but this one's about a new patent developed by Geobear, and Andy's going to run through some slides now. So there's going to be a Q&A at the end, so if you've got any questions, I'll enable a Q&A mode in the chat in the bottom right, and then we can come to those at the end. So I'll hand over to Andy now, and I'll join you after.
Okay, thank you, Alistair. Okay, so I'll just do a bit of an introduction as to who Geobear are for those people who don't know. So we're a leader in non-disruptive solutions for foundation infrastructure, settlement and substance problems. Global business established 1983 in Finland. Company was known as Eurotech till December 2017 before global rebrand to Geobear. UK business established in 1989, and we currently have offices in Wolverhampton, Winchester, and in fact Hatfield, not Sandy. We have a full in-house design team. We also work with third-party consulting engineers, material testing labs, and geopolymer technology has been installed in over 250,000 projects worldwide. So it's a well-known solution. Just to show the global reach of the company, although I'm based in the UK and probably 75% of the business with Geobear is in the UK. We do a lot of work in other countries. And we operate in different sectors, including highways, commercial developments, residential properties, energy utilities, airports, ports and harbours, and railways. And today's topic is mainly about railways. So, and specifically about transition zones on railways, which is an interesting topic to talk about. Just to give you a brief overview of the general capability of what geopolymer can do. So the general things that the technology is used for is ground improvement, increased loading and settlement reduction. Both of these things relate to transition zones. It can also be used to mitigate clay shrinkage treatment. This is seasonal swelling of clays under houses or on embankments, railway embankments as well, underneath commercial properties. We can lift slabs, stabilize concrete slabs and lift buildings and structures, then filling voids with natural or whether they're man-made, such as tunnels or culverts, lifting buried pipes, excluding water from excavations and creating impermeable barriers, stabilizing sinkholes, mine workings and shafts, stabilizing tunnel linings. This relates to the sort of rail sector, slope stabilization, as I've mentioned, transition zones to bridges, which is today's topic, railway ballast stabilization, liquefaction mitigation, which is more relative to the United States and parts of China rather than the UK. Compensation grouting for tunneling, reducing vibrations, and we can create power poles, which are structural stabilization of buildings and containment of mobile contaminants. So there is a Geobear capability matrix on our website. So if you want more details and exactly what the sort of performance range is for the geopolymer solutions we offer, I would direct you to go and have a look at that. I'm not going to go through the detail now, but we try to define what we can do, what we can't do. So that all information you might need is there. I'll do a brief introduction to what geopolymer materials are. So Geobear geopolymer is based on a multi-component structural resin technology, which is specifically developed for ground engineering applications. It's based on polyurethane technology. And the geopolymer mix undergoes exothermic chemical reaction, which induces a state change from liquid to solid. It's a consequential increase in volume, which produces a dynamic energy in subsequent expansion force. So we inject as a liquid, two-component liquid, reacts in the soil and creates an expansion. And in that expansion of the polymer densifies the soil or can strengthen soft clays. The chemical reaction is very quick, and the immediate resulting solid compound possesses definitive physical and mechanical characteristics. So we know how strong the material is when it sets in the ground. Geopolymer will reach 90% of its final mechanical characteristics in less than 15 minutes, so it's very fast acting. As a result of a lot of research over many years, we have about 22 different polymers, which we can select depending on the project and the solution that's being developed. So we have a wide range of different polymers, which we use for different applications. There's a little clip here that Alice is going to show, which shows how the liquid geopolymer will expand into a void. Okay, so what you saw there is the liquid geopolymer entering a void or a cavity and it rapidly expanding into a solid material. This is in the video we're using a particularly highly expansive geopolymer that's more suited to filling in voids. The rate at which the geopolymer expands is controlled by the chemical composition of the resin, and that can be varied to get a different reaction time. So there's a graph here that sort of shows how the geopolymer behaves over time. So after mixing, you mix these two components together, and there's a period of time where nothing appears to be happening. That's called the cream time. So that is a time in which the catalysts which are in the mix are beginning to start the reaction process. So there's a period of time where the geopolymer is in the liquid condition in the soil. That cream time can be as small as 1 second. It can be as large as sort of 15 seconds. So there's a time over which nothing appears to happen. Then the chemical reaction kicks in and there's a rapid increase in volume and a rapid increase in viscosity. And that's as the polymer's going from liquid to solid state. And there's a consequential increase in volume and a consequential reduction in density, because geopolymer materials in situ are generally low density materials. The maximum density you normally see in the ground is not much more than 300 kilograms per meter cubed. It may be 120 more often. Very rarely it might be as high as 1,000, but that is the maximum it ever really gets to. So it's generally less dense than soil. So this shows a cross-section blown up using an X-ray microscope to see the internal structure of the geopolymer. And what you see here is sort of bubbles, if you like, or you can see rings of white material. That is the actual resin. And then inside the resin, there is a gas pocket, and it's the gas pocket which is filled with carbon dioxide, and that's what drives the expansion. So the actual geopolymer foam is comprised of hard resin and carbon dioxide pockets or bubbles, and it's the ratio of a resin to the bubbles that controls the strength. So when there's less bubbles or they're very small, there's more resin per unit area, and that means there's more strength. So when you look at the compressive strength of geopolymers, you can see that the strength increases with the density. So that means there's less gas bubbles, if you like, and there's more resin per unit area. And so you get an increase in strength. More resin, more strength. Same thing is true for stiffness or Young's modulus. As the density increases, you get an increase in stiffness, really just because there's more resin versus bubbles of gas. So when there's very, very small amounts of gas present in bubbles, you have maximum strength of the material. So how does geopolymer work? The picture here shows a cross-section through an excavation in clay where geopolymer has been injected. And you see that the geopolymer here is forming what look like lines or planes of white material against a grey or brown background. And that's actually fractures in the soil that have been filled in with hard geopolymer. So the injected liquid geopolymer will penetrate and spread into a soft clay via a phenomenon called hydraulic fracturing. The polymer extends into the fracture and undergoes a state change from liquid to hard solid geopolymer. The solid geopolymer reinforces the soft clay and increases the bearing capacity and the stiffness modulus. And that's on a volumetric ratio of polymer to clay. The more geopolymer you put in, the more strength you get, almost directly proportional. That's how you reinforce cohesive or soft clay materials. And this just shows the relationship between the swelling pressure and the soil confinement pressure. So as the geopolymer expands in the soil, there's a resisting force from the surrounding soil. And where those two pressures are in balance, you establish what's called the equilibrium pressure. And that's the point at which the geopolymer hardens in the soil. And if you know the equilibrium pressure or can calculate it, it allows you to calculate the in situ density of the geopolymer, from which you can calculate its strength, from which you can calculate how much ground improvement you're going to get. So determination of equilibrium pressure is a very important part of the design process. And if you imagine a line of geopolymer injections in clay which form these fractures, and if you arrange them in layers and you arrange them in lines, you build up a network of reinforcement planes through the clay. And this is really how it works. You generate these layers in 3 dimensions of reinforcement within the clay. That's how you end up with a higher bearing capacity and a higher stiffness. Now, in granular soils, the process is slightly different. Injected geopolymer will permeate through the pore space, forming what we call a bulb, and then that bulb will expand. So we have a process here where there's an initial injection into a granular soil, and there's no expansion. This is the cream time. And then during the gel time, there's expansion of the geopolymer within the granular material, and it starts to expand. And that expansion causes what we call a plastification zone, which is really a zone of densification around the expanding geopolymer bulb. So on completion of injection, you have a hard bulb of geopolymer, and surrounding that bulb, there's a zone of plastification or densification. This is where the soil has been physically moved out of the way. So when you actually arrange your geopolymer injections in rows or grids, that plastification zone is superimposed on other plastification zones, and you get densification. So this is how you get a densified zone in between the injection points. And that's how you basically compact granular soils. So let's get into the main topic of conversation, which is the UBC4 case study. So UBC4 is a rail bridge over a road, over Sarsfield Road in Dublin. And here you can see there are 3 roads or rails on the bridge. And so UBC4 is a single span structure on the Dublin to Cork line at 1 mile 0638 yards. The bridge carries the railway over the Sarsfield Road. The superstructure consists of a silent bridge deck on 4 number longitudinal steel box girders supported on RC bearing shelves. The bridge deck is askew to the direction of the track. Because of this, there is a perennial SS defect for twist at the transition point, It was renewed many years ago. The rail and fastenings at the twist point are showing signs of distortion because of the differential settlements encountered at the bridge abutments. The track requires frequent maintenance as a holding measure, but the geometry faults cannot be fully rectified until a suitable transition is provided. So this is a common issue, is where you move from embankment fill materials onto a hard structure, such as the wing walls of a bridge abutment. There's a rapid change in stiffness between the abutment material and the embankment material, and that causes defects because of differential settlement. Now, I think we have a little video to play now that shows you the deflection at the transition point, which Alistair can play. So there you can see the track bending down as the train moves over the point between where the abutment stops and the soil begins, if you like, underneath that ballast. So you see there's a deflection. Now, the objectives of the ground treatment or ground improvement, as defined in the works information, was to create a consistent zone of track bed stiffness on both legs of all three roads to achieve long-lasting compliant track geometry. The minimum starting stiffness should be between 50 and 80 MPa and should increase in the direction of the bridge abutments, such a transition zone would be created. This is the objective set to Geobear. So there's a ground improvement design process that you go through in order to determine how you can create a transition zone using geopolymer. And so the first step is to define the ground model and validate the ground model. And that includes a review of all available ground investigation and track data to understand, the geology and then the geotechnical parameters you're going to assign to the different layers within your model. Second thing to do is to determine the length of the transition zone, which is a function of the line speed. And then third is to determine the depth of treatment. Now, we did that using Plaxis modeling to look at the stress zone to see how the stress moves through the ballast into the underlying subgrade. And then you need to determine the geopolymer injection mass and the spacing of the injections to meet the objective, which is the stiffness as required. And Geopolymer has in-house design models which are based on theories developed by a guy called Manacero and his colleague Dominengiu, and the Italian professors who've done a lot of work on geopolymer design. So this just shows you a quick overlay of the bridge, and where we had some investigation points. So we had a series of boreholes, and we had some sort of like inspection trial pits done in the track bed itself, and also some dynamic penetration testing was done to work out the existing stiffness of the soil. And so based on a review of all of the site investigation information, we're able to develop what we call a ground model. And so the ground model that we come up with is broken down into layers. So, and if we name those layers going down, we have the ballast on the top, and underneath that was a sub-ballast layer, which is really a sand. And then below that, the actual embankment is made out of fill, and it's made out of clay fill. So it's not a granular embankment, it's a clay embankment. And it's, if I remember correctly, it's sort of a soft becoming firm, becoming stiff, sort of a silty, gravelly clay. It's probably made out of reworked local boulder clay, looking at it. But that's essentially what it is. It's a clay fill. And it was noted to be quite soft underneath the sub-ballast. And then the stiffness of that clay fill embankment increased with depth until he got down to the underlying natural boulder clay or glacial till, and that was quite stiff, a shear strength of 100 or so. And that extended down some depth until he got to limestone bedrock. So the area of interest for us is really the area, the sub-ballast and the area immediately underneath it is that clay fill. This is what has been softened, and that is where we're seeing a transition problem developing because that clay fill has been weakened over years, either through rainwater ingress or just the dynamic loading of the train causing that top to soften up. So that was our ground model, and that ground model was developed looking at the site investigation data, looking at the SPTs that we had, looking at the laboratory test data to come up with what looked like reasonable parameters for modeling, and those parameters being shear strength and Young's modulus. So then we need to check, is our model right before we go on any further in the process? So we did model validation. And so the validation of the input parameters to the geopolymer ground improvement model was done by analysing the track deflections observed from video footage, and I shared that video footage. Now, we used image correlation techniques using a computer software to analyse the track deflections that you saw, which were caught on the video recording. And from these, it indicated that the vertical rail dynamic deflection was about 5.4 mil. It may look like it was more than that on the video, but we analysed it sort of screen by screen to work out how much is it actually moving. So that's roughly the dynamic deflection, about just over 5 mil. And a dynamic analysis of the assumed trade loading combined with the average ballast and sub-ballast thicknesses indicated that the modulus of subgrade reaction would need to be around about 11.7 MPa to generate 5.4 mil of deflection. And that's sort of in good agreement with the ground model. So if I go back and show you what we assumed that the E of the top of the clay fill was 12. That is an assumed value based on the site investigation. We then did this modelling using some specialist software we have and indicated it need to be 11.7. So that's, as far as I'm concerned, that's the same number. So the model that we've got in terms of the stiffness appears to match the sort of deflections you get that were observed by the train going over the bridge abutment. And this shows that a graph of that deflection. This is 5.4 mil deflection here. So the next thing is to to construct a transition zone model. So the idea here is to, if you like, build into Plaxis the existing ground conditions, and also to sort of determine what the settlement and strain would be under some sort of loading. Now, analysing a dynamic load is quite difficult, so we took a conservative approach of putting on top of the rail sleepers a very high static load, as the dynamic loading would have been lower, but we went for a more conservative approach to put on top of our sleepers a high static load to see how that generates strain in the underlying soil. So that's how we built up our model. Now, the design length of the transition zone is taken as 50% of the line speed in meters per second, according to Burrow. We have a reference for this. So at a line speed of 60 miles an hour, which is 26 to 27 meters per second, the transition should be 13.4 meters long. And we use a design length of 13.8 meters. So the length of the treatment zone, where we're going to increase the stiffness of the soil, roughly just under 14 meters. That's how we determine that. We then ran some strain model results in Plaxis to see, well, where is the strain happening? So remember, this is a static model using a high load, probably higher than would normally be experienced by the sleepers. And the Plaxis analysis is indicating the vast majority of the strain and displacement occurs in the depth zone up to 1.5 meters below the subgrade. So, and the very high strain is in less than half a meter below the base of the ballast subgrade. So the red is high strain and it diminishes with depth. But this is indicating where is the strain really developing, and it's developing in the near surf, so just underneath the subgrade and the ballast. So this is a zone we need to target primarily, but we were going to do a deeper treatment to make sure we covered off most areas where there's some change in strain. And so based on this analysis, we're looking for about a treatment depth of 1.5 meters. The top 1.5 meters of subgrade would be treated. And then the likely effectiveness of the treatment was then calculated in Plaxis. So what we then did is, through a process of iteration, is to increase the predicted stiffness of the soil after treatment and put that back into Plaxis to see what would the effect be in terms of strain. So this is an iterative process where you go backwards and forwards adjusting the shear strength, and the way you adjust the shear strength is by adjusting the amount of geopolymer you put in the soil. As I said, it's relatively proportional. So the more geopolymer you put in, the more stiffness you get. So through a process of iteration, and it took several steps in the process, we got to a point where the modelling was indicating the rate of deflection over the transition zone would be 0.25 millimeters per meter, which is within the accepted range of 0.4 millimeters per meter according to Sharp. And they'll have a reference which is at the end of the presentation. So we essentially use an iterative design approach to come up with soil parameters where the rate of change of strain is within an acceptable range. So that's the sort of process we go through. That now leads on to what does a treatment plan look like. So, as I said, we calculated the amount of geopolymer you need to put into the soil to get an acceptable performance in terms of rate of strain. And that means injecting 13.8 meters either side of the bridge abutment on each of the different tracks. And we broke that distance down into zones. So what you see on this bottom section here, we have zone 1, zone 2, zone 3, and zone 4. So as you approach the bridge abutment, we basically inject more geopolymer into each zone to get a transition. So we want the soil to be stiffer very close to the bridge abutment and less stiff further away. So we basically varied the injection amount, the quantity, into each of the injection points as you approach the bridge. And for convenient reasons, we actually did that in 4 different sections. So we increased the mass of geopolymer injection in a steady and controlled manner in these different sections. So across each sleeper, there's 4 injections, and there's an injection in between each sleeper within the transition zone. So this shows you in cross section what that looks like. So we have our injections going down, and we have them going across the sleeper. So each sleeper bay required 4 injections spaced at 866 millimeter centers on a sleeper length of 2,600 millimeters. The injections between the bays would be approximately 662 millimeters center to center. The depth of injections were set at 0.1, 0.6, 1.1 and 1.6 meters below the sub-ballast. So that's the sort of the depth of treatment, roughly 1.5 meters in the top of the subgrade. And the injection quantities were varied. So I showed in the different subsections what the kilo amount would be. So in subsection 1, we had 3 kilos per level. In subsection 2, we had 4 kilos. And in subsection 3, 5 kilos. And then in subsection 4, 6 kilos. So we effectively doubled the amount of geopolymer from the first zone to the last zone. So we're increasing the mass. And by increasing the mass, you're increasing the stiffness. And these quantities and the model prediction outcome for strength were what were put into the Plaxis model to show the change in the strain. So in terms of field implementation, so these works were undertaken over 19 limited nighttime possessions during November and December 24, eliminating the need for traditional excavation track reconstruction, which would have required several weeks of line closures to execute. During the injections, the track bed was monitored for lift using laser levels within an accuracy of 0.5 millimeter to ensure no overlift occurred. The works were carried out safely with no reported injuries or incidents. And the total number of injections holes drilled was 528, and approximately 10 tons of material were put into the embankment. And the key thing here is this has all been done at night in very short possessions, maybe less than 5-hour possessions to actually get the work done. So there's literally no impact on the operation of the railway during this treatment. So here's a graph of we verified the strength increase using DCP dynamic probe testing, converted that into shear strength and shear modulus. Soil modulus. And I plotted the results in plan, the results that we got. Now, verification of the increase in soil modulus was determined by dynamic cone penetration testing. A total of 12 DCP tests were undertaken, with 6 between sleepers 8 and 9, and 6 between sleepers 18 and 19 on the sort of general track. Testing was done on each side of the bridge. The results show that the performance target of 50 to 80 MPa had been met in 11 of the 12 positions at the start of the transition zone, increasing to 100% of positions at the end of the transition, with a generally consistent increase in Young's modulus achieved on all tracks. So there's only one point where the starting modulus was under 50, this one over here at 46. All other points it started at above 50, and in all points the modulus ended up above 80 by the time you got to the actual bridge abutment. So overall, we'd sort of met our project brief on the actual stiffness. What sort of matters was the results of some track monitoring. So Irish Rail did run track monitoring over this bridge, and the track monitoring was carried out before and after geopolymer treatment. Results are in that table, and no tamping was carried out between the track monitoring events. Analysis of this data of the before and after. The before is on this side of the table. The after's on this side of the table. You can see there's less red on this side and on this side, and there's less yellow on this side and on this side. And green means it's an acceptable pass. Red means it's significantly bad, and amber is like a warning condition. So analysis of this data indicates that there was a reduction in short twist and long twist warp at between 59% and 69% of the rail positions, and a downgrading from red fault to yellow or green at 75% of the impacted rail positions. So overall, there was an improvement in the track monitoring, and we're advised by Irish Rail that they're quite happy with this performance, and that the line speed could be restored based on this. So, in conclusion, this case study sets out to demonstrate how the impact of track faults at transition zones can be mitigated via the injection of expansive geopolymers to increase the stiffness modulus of the soils within the zone. The major advantage of this approach is to minimize the impact on the operation of the railway by executing the remedial works within limited nighttime possessions. The design of the ground improvement is based on theories developed by Dominici and Manacero, which describe how hydraulic fracturing of clay soils allows the fractures formed to be filled with expansive geopolymer, which undergoes a state change from liquid to solid. Calculation models were used to design the quantities of geopolymer and the injection layout required to achieve the required increase in stiffness modulus, which was subsequently proven by post-treatment dynamic cone penetration testing. Subsequent track monitoring showed there was a reduction in short twist and long twist warp at between 59 and 69% of rail positions, and downgrading from red fault to yellow fault or green at 75% of the impacted rail positions. Most importantly, all of the work was carried out within 19 limited nighttime possessions without any health and safety incidents. The work has improved track safety and operations by reducing the twist and warp faults without unduly impacting the operation of the line. And that is the end of the presentation. I've gone through that fairly quickly to leave a little bit of time for questions. If we have any questions, we're happy to take those now.
Thank you very much, Andy. Yep, hopefully everyone found that really interesting, which it clearly was. So there is a question come through, so I'll put this straight onto the screen. And then we can pick that up. Bridge abutments are normally backfilled with drain material and have backwall drainage, etc. in the backfill. What were the thoughts of injecting geopolymer potentially blocking the free drain in the backfill?
Well, it's not clear whether such a bridge abutment had such free draining material. I mean, this is a very old railway line, probably constructed, in the 1800s. So I think understanding of proper drainage behind bridge abutments wasn't probably fully understood at the time this bridge was constructed. There was no indication from the site investigation any such layer actually was present. So if there is drainage material present, well, that needs to be looked at, because if you've got granular material as opposed to clay material, then we'd need to use different geopolymer. And what you should note is that you never fill all of the pore space using a granular, when we're doing granular soil compaction. So in densifying granular soil to increase its stiffness modulus, there's always gaps left in between where the geopolymer bulbs are. So generally speaking, the overall permeability of granular materials is not significantly affected by geopolymer injection unless we put in a very large amount and we're designing for that outcome. So if we're trying to prevent water flowing through granular material, we'll design the work in such a way as to do that. But if we're not trying to achieve that, then the spacings that we use will ensure that material remains to be free draining. Hope that helps answer that question.
Yeah, thanks, Andy. So, Martin, was any monitoring carried out on the bridge abutment during the injection?
A short answer was no, there wasn't any monitoring carried out on the bridge abutment to my knowledge. We were monitoring the track and whether the track was moving or not. But whether any monitoring on the bridge itself was done, no. But the loads generated by what we're doing on the bridge abutment, when you look at the distance we're injecting from the bridge abutment, would not be significant.
Okay. And then Martin had another question, actually. So is this system approved for use on Network Rail?
Well, we've done work with Network Rail, on various different types of projects. We haven't done a transition zone project, but that's because I think we haven't been asked to do one. But we've done a lot of slab track reinforcement for network rail. We've done ballasted track improvement in terms of subgrade, and we've also done a lot of work on tunnels for network rail, strengthening tunnel linings, and we've also done some work to stabilize unstable ballast as well. So not yet, but we do quite a lot of work for network rail. So and I think they will on a project by project basis, they will accept geopolymer solution, and they going through the normal design approval process.
Yep. Hopefully that answers that question for you. So how well does the geopolymer work in soil that is very wet? So that's not come through as a question, that's in the chat. So saturated material, how well does the geopolymer work? That's from Zahid.
It depends what problem is you're trying to fix. Now, the only soils in which geopolymer is possibly not the right solution is highly organic clay or peat. Generally speaking, if the soil is wet, we can do work underneath the water table, and we routinely do so. We densify fully saturated sands quite commonly, and very soft clays, which have a high moisture content. So the only thing to be mindful of is if there's a very high organic content. And if there's a high organic content, we need to use a lot more geopolymer than normal. So it might not be the right solution, depending on what the objective is.
Yeah, thanks, Andy. So I believe that's all the questions. By Chow, he asks, so can I mark this as a question? No, the question's not working. But he says, I suppose Geobear or the geopolymer is risks registered for network rail projects.
It's approved on a project by project basis. Yeah. There's no requirement for formal product approval, and we've been through this with network rail, that it has been approved and has been used on several projects that I mentioned, and those are approved on a project by project basis rather than as a general product approval, because you have to do the design for each project. It's not like we're putting in place concrete culverts or something, which is the same every single time. All geopolymer designs are different, and they're done on site-specific conditions.
Yep.
So that's the way we normally approach working with network rail.
Okay, and then Chris asks, how much geopolymer is injected per point?
Well, on this particular project, it was between 6 and 3 kilos per point. But that's just on this particular project. So it will vary depending on what the objective of the exercise is.
Yeah. Okay, that's great. That is all the questions, Andy. So appreciate you answering those and running through the presentation. Thanks for everyone that joined us online today. The next webinar we have is on the 12th of September. That's looking at clays specifically and the performance of our Geobear or geopolymer solutions in clay soils. So that's particularly interesting and relevant to the railway as well. I'm going to send out an email after this. If you've got any other questions, please just come back to me. And we hope you found that interesting. So thank you very much, Andy, and we'll see you again on the next one.
Okay, cheers, bye.
Thanks.